This is X3, question 19. And in this question, there is a table. And the table is not the complete data set. The data set is repeated. So the first row, so a data item like this is repeated 5 times in the actual data set. So the actual data set has size 23, so it's the sum of these numbers. And these are basically the number of times each row is repeated. So when we add up the counts, we add up the actual number of days instead of just counting the fraction of times that these things happen. Okay, so here we're asked to compute the probability. So of course, using maximum likelihood, it just means count the fraction. So we're counting the number of times. We have rainy, which is n, and then warm, which is n, and then bighorn y. So we're counting the number of y, n, and y divided by the number of n. So that means we're dividing it by the number of n plus number of n y. Right? So the reason we want to do that is the sum of this is just the number of times rainy is n and warm is n. And we don't care what this bighorn is. Okay, so there are 2 things we need to count. N and y, which is which one? This one. N and y, and the number is 3, so we just use 3. And if we have smoothing, then we add the smoothing parameter. And on the bottom, we have n and n, which is the first line, so it's 5, plus n and y, which we already have, so it's 3 over 8. And again, if we do Laplace smoothing, then we add 1 on the top and add 2 on the bottom, because there are 2 possible values for y. I mean, not y, for bighorn. So that's this. And the next one is, we actually didn't talk about this kind of question specifically, so you need to combine 2 topics. One is the Angren model, which looks like this, and the other one is the Bayesian network, how many conditional probabilities we need. So here these are actually conditional probabilities, and when we store them, we don't need the one, we don't need the last one. So in particular here, the probability of Wn being equal to, since the vocabulary size is 94, so the fact that it's equal to 94 given all the other ones can be computed by the other ones. So basically 1 minus W is 1 given the same thing, minus probability of Wn is 2 given the same set of things, and so on, until probability of Wn is 93 given, again, the same set of things. So in particular, for each of these sequence of n-1 words, we need to store 93 conditional probabilities. And the question is, how many of these do we need? Each one can take 94 numbers, so we have n of them. So, I mean, not n of them, n-1 of them, because it's starting from 1 to n-1, so that. And here we have a 4-gram, so n is 4, so it's just 4 minus 1. So that's the number of conditional probability we need to store in the CPT table. And again, we only need, given a fixed set of previous 3 words, we just need to store 93 probabilities because the last one can be computed. But for all of these 94 to the power 3 combinations of the things we're given, we cannot compute each other. So we can not compute one based on the other combinations. So we need to store all of these. So that's why this is the answer here. And the next question that not many people signed up is the I think it's usually called the boy or girl paradox. So the story here is there are two families. They both have 5 kids, and for one of them you saw a children and she's a girl. And for the other family, you only know that at least one of them is a girl, but you don't know which one. So you haven't seen a particular child being a girl. So the problem here is, what is the probability that each of these families has at least one boy? So that when we are asked to do these kind of probabilities, we just do 1 minus the probability we have all girls. So there are 5 child. So it's G. And the probability here is basically the number of combinations when we have this, which is always 1, divided by the total number of possible combinations for both families. So let's start with the Smith family. So for the Smith family, we know one particular child is a girl. So suppose, let's say, the third one is a girl. So we know that the third child is already fixed. So how many possible arrangements there are would be the first child can still be boy or girl, the second boy or girl, and the fourth and fifth one as well. So if you count how many combinations we can have, so for example, we can have B, G, G, B, G, or you can basically list out all the possible ones. We notice that since this is fixed, we only have 2 to the power 4 possible ways to basically assign the other kids being either a boy or a girl. So these are the total number of possible arrangements or possible permutations, and only one of them is all girls, so 1 over 2 to the power 4. So that's the probability for the Smith family. And for the Wood family, it's still 1, so there's only one combination or one permutation where all the 5 kids are girls. However, since we do not know a specific child is a girl, we only know that there is one of them is a girl. So we have only eliminated one possible combination where they're all boys. So it's basically all possible ones minus the B, 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 1. So we just count all possible ways to assign boy or girl and subtract one specific permutation, which is all boys, because we know at least one of them is a girl. So that sentence only eliminates one of the permutations, but the fact that you saw one specific child being a girl, that eliminates 2 to the power 4 number of permutations. So that's kind of the main difference. And there are total 2 to the power 5, and we're subtracting 1. So it's 1 over 2 to the power 5 minus 1. So that's basically how we compute these probabilities. Okay, and the next one is you have a join probability table over 6 random variables. Each one can take on values 1 to m, and if we want to compute the probability x1 is 4, then what that means is we need to sum up over all possible values of the other variables, so x2 being 1, 2, 3, 4, and also x3, x4, x5, x6, all of them can take on value 1, 2, 3, 4. And we sum up the probability of x2 equal to x2, x3 equals to, so these are random variables, these are specific numbers, so these are capital letters, and these are small letters. And x6 equal to x6. So we sum up all of these probability. Each one is called the join probability. And the question is just asking how many of these ones there are in the sum. So if you look at the sum is over all combinations of 4 values for 2, 3, 4, 5, and 6. So it's 4 times 4 times 4. And there are, how many of them? 5 of them. So 4 to the power 5. Because we know x is 4 already, so there's only one combination, so it's kind of 1 times that. So the answer, how many we need, is 4 to the power 5.